Okay, so now we found some kind of a bound on the b and k value, right? That's what we did in the previous video. And we are going to build on that. Basically, we are going to fill the table values here where we have like the n values tabulated here and the k values up there. And we saw this table earlier, and we know that bn1 is 1 and bn of n is 2 to the n minus 1. And we also know why that's the case. And if you remember, we also filled these values, right? So let's not think about those, the upper triangle. We are bothered about these values, the lower triangle. And if we go back here, we already have this equation here, and using this, basically we have some kind of a recursive equation for the bound for bn of k. And we can start filling the table values now, right? So let's actually do that. And how will that happen? Now, if you look at this equation itself, it's essentially beginning with bn and k, obviously some n value, some k value. And the bound for that is going to come from some of the previous values from n and k values that we have in this table, right? And that's why we are saying that this is a recursive equation, and we can start filling the table values so that we have the upper bound on b and k value, right? And if you think about it, so here we're starting to fill this up, and this is, by the way, the equation that I was talking about, right? We came up with this for any n and for any k, and once we have that, right, we know that it's a common practice to break down a larger problem into smaller, easier versions, and especially if it's a combinatorial problem, and then build on that. So that's exactly what we're doing here. So here, this is B32, right? So this is B32, right? And the upper bound for that is going to be less than or equal to this is 2 plus b, again here, looking at this, I'm just like looking at this equation and like filling this up. So n minus 1 is going to be 2 and k minus 1 is going to be 1. Now we already have these values from the previous, like the table that's already filled in, right? So for example, I have like this value here, which is b2 of 2, right? So I have this, and I also have this value here, which is b2 of 1, right? So I'll just add them up and I get 4. Similar to that, I can fill this here, this is this place here is going to be B43, right? And that is going to be less than or equal to B32 plus B33 and B32, right? Which is essentially this and this. So this is going to be 11. Now, if you remember from one of the earlier examples that we looked at, right? We found, like, we started with saying that B43 is actually 11 dichotomies, right? And that's the max that you can get. And that's what the value will be here. Similar to that, this one here is going to be 5. Why? Because I'm going to add this and so on, right? So we'll keep doing that, and we can go on and fill this table up, and it will look something like this. Right, again, like this is emphasizing the fact that we looked at B43, and we saw that the maximum number of dichotomies in that situation. And if you remember what B43 is, it's essentially telling us, given endpoints, we don't want to shatter any subset of size 3, right? And the max number is 11. Now, all of this is good. We can just like keep on filling this table, but the like some kind of a drawback here is that this can get tedious, right? Because we are combinatorially filling up this table, and we have to have the values from like the previous bn minus 1k and then keep building on that, which is not quite the solution for cases with like larger n's and larger k's. And of course, like we can keep doing that, but we need an analytical solution to this, right? So we need an analytic bound. Okay, so how do we come up with that analytic bound for the quantity bn of k? Okay. So this is a theorem, and this is also there in the book. So I'm going to state that here. The theorem states that Bn of k is less than or equal to the sum of all i's starting from 0 up to k in choose I. This is the theorem, and that kind of establishes this analytic bound. Now, you might be surprised, right, by this value, how this value came up. right? Where did this value come from for this bound? Well, if you remember the bound itself, and let me write that down here again. I know that I'm repeating myself, but that's fine. Because if you look at the bound, you will be able to figure out that this is the outcome of something that's known as the Pascal's identity, right? So the Pascal's identity can also be visualized or written in terms of the binomial coefficients, and that's exactly what we're doing here, right? So if you've taken any discrete math class, you might know that. If you've taken Fox, even then you know that, right? So, but again, I'm going to restate it here. If you look at these quantities like this Bn of k, this is actually the binomial coefficient for n choose k. So what this is saying in terms of those coefficients is n choose k, where n choose k is actually equal to n minus 1 choose k plus n minus 1 choose k minus 1. Okay, and the proof of this is usually done in discrete math courses, but I can quickly give you an overview of how the proof is done. So basically the left-hand side here, right? And I'm not doing a very comprehensive proof, but just like to give you an idea. So here I'm saying there are n things and I need to choose k. So the number of ways of choosing k items given n items, right? So what I can do is, let's say I have like these n items, right? And there are two possibilities when I start choosing items. So the first possibility is that I select this item, right? So I selected this item. And then the rest of the choices that I have is that I have n minus 1 items left and I need to choose k minus 1 items. Remember the original problem was n choose k, which means I had n items and I had to choose k, right? So this is the first possibility. The second possibility is that I do not choose the first item, right? But I have like all the possibility of like these n items again. So basically I'm left with n minus 1 items, but I have to still select k because I just like rejected the first one, right? So that's how we come up with this equation here. It's essentially the sum of like n choose k is n minus 1k plus n minus 1, sorry, not plus, n minus 1 choose k plus n minus 1 choose k minus 1. Okay, so that's that, but now we are coming back to our original theorem and how to prove that. And of course, there is a detailed proof given in the book, but we are going to see and like basically go through that. So the proof for this one is via induction, given that we have this identity with us. So let's look at the proof by induction. Okay, so the way the proof by induction works in general is that the first thing we do is that we verify it for a base case, which in our case is n equals 1. So that is our base case. And then we hypothesize it for some given case, which in our case is this one. This is our hypothesis essentially. So we are saying we verified it for n equals 1, which means B1 choose 1. So we can like see that the statement is true. B1 1 is less than equal to 1 choose 0, because 1 choose 0 is what? It is 1, right? And we have verified this before, if you remember. B1 of 1 is 1, right? So this is true for n equals 1 and k equals 1. So that's my base case that has been established. Okay, the second one is that assume this identity holds, or it is true for all n's and k's, such that this is true, right? So this is something that we are assuming. Now what we need to prove is that for all n plus 1s and all k's, this is true. This relationship is true. And if we are able to prove that, then that is going to complete my proof by induction. That's how we prove by induction. And I think in one of the assignments, you will have one of the problems where you'll be asked to prove something via induction, and that's how you should do that. Okay, so having said that, let's actually move forward. Now we already know this identity, this lemma, right? We just proved it in the previous slide. So I'm going to use that. The only difference here is that I'm saying n choose k plus n choose k minus 1 is n plus 1 choose k, right? So I've just like rearranged the few terms. Now, remember, I have to prove this, right? So I have to I have to prove for this, like only the left-hand side. I have to prove that this bound, like the polynomial bound here, it exists for n plus 1 choose k as well, right? Now I'm beginning with my basic equation, right? I already know that this thing is something that we proved earlier, right? We proved this earlier already. I'll just write already, right? We already proved this. So I'm beginning with that. So I'm saying this bn plus 1 choose k is less than equal to bn choose k, or I shouldn't say choose here because it's the maximum number of dichotomies given some points and some subsets. So let's call this bn plus 1k, and this like right hand side is going to be bn of k, bn k minus 1. Now, given that we have established that this is bn choose n of k is actually n choose I, the summation of this, right? We have like established, like we are assuming that this is true here in the second step. So I'm going to replace it by that, right? And I'm going to replace this thing by this here, right? So that's what we begin with. Basically, we're applying the induction hypotheses to each term on the right-hand side. That's a better way of putting it or stating it here. Okay, so moving on, what we're trying to do is we're trying to take out some terms common here, right? So I have like rearranged, instead of I equals 0, if I start summing up these terms starting from I equals 1 up to k minus 1 instead of k minus 2, all I have to do is n choose I minus 1, right? So this is a little rearrangement here. And here, this term comes out of the fact that we proved this already here, right? So I can take out the I equals 0, 1 from this, right? And that is that is going to be 1. So that's all I've substituted like step 1 from here. Right, so that's 1. But how does that help us? That helps us because then I can have the common summation for both the terms, right? So I have like I equals 1 for both of them, and I just like take them out. And what I'm left with inside is n choose I plus n choose I minus 1, right? From the lemma, from the identity that we have already, right? This will reduce to n plus 1 choose I, right? Pascal's identity, already proved it, so that's that. And if we want to take this 1 inside, that's only going to amount to I equals 0 up to k minus 1, and this is what we get, right? So basically, this is telling us that this left-hand side, this bn plus 1 choose k, is essentially less than equal to this term, which is what we wanted to prove, right? So this kind of proves what we wanted to prove. This proves the analytical bound here, and that's pretty much it. We proved it by induction. This is going to be really important. And let's move further and see that there are certain other identities that again can be proven by induction, but I'm just going to state them. And the statement of those identities is important because remember, we are trying to create some kind of a relationship between this quantity, this b, and if there is a relationship, if it has a polynomial bound or not, right? That's what we are trying to do. Now, let me state those known identities and then we'll move forward from them. This is also a theorem and you can definitely go and prove it by induction or by some other method, but I'm simply stating them because we need to use them, right? So the first identity that we're looking at is I from 0 to k minus 1 n choose I is itself bounded by this quantity n k minus 1 plus 1. That's the first identity that we need. The second one that we need is if, and this is a slight sort of a modification, and both are true, and there are other identities as well that establish that this term here, the summation of this term is bounded by a polynomial bound, essentially, right? So I equals 0 up to k minus 1. This is something that we know, right? And we are going to utilize it. N choose I is also equal to E n k minus 1 to k minus 1. As I said, why is this important? Because we are trying to create this link, right? So the whole point of showing you these identities is that the quantity on the right hand side is like the quantity on the right hand side in our analytical bound here, this thing, right? It is bounded by a polynomial. So indirectly, what we are trying to establish here, indirectly what we are trying to say is that this b n of k, right, is bounded by like one of these. So I'm going to pick the common convention is to pick the first one. and I'm going to go with that, right? So nk minus 1 plus 1, right? So we have like many choices. I have like this choice, I have like this choice, but I picked this one up. Okay, all of that is fine because now I'm able to establish some kind of a polynomial relationship, right? Now, we are not done yet because our goal was to somehow create a polynomial bound for my growth function, if you remember, because it was the growth function that was really impacting my error bound and was impacting my learning problem. And that's what we want to do, right? So let's move on towards that process. Um, Let me redefine Bn of k so that we are clear on what this was doing, right? So this is the maximum number of dichotomies on endpoints so that no subset of size k is shattered, right? And now we know that it is bounded by some polynomial in n, right? So this is some polynomial in n, okay? Great news for us. Now, as I said, the real issue was the learning problem and not just this, right? So let's go back to the learning problem and link this quantity to the growth function. And for that, we'll have to somehow review a little bit of the growth function and look at the examples that we looked at earlier and then go from there. So that is going to take a little bit of time. So I will just stop here and then maybe move on with the same discussion in the next video.